Hey, it's Mr. K. We're doing a video for AP Physics 1, and we have a velocity time graph of some random object. And so this object is staying at a constant velocity, it is speeding up, it is staying at a constant velocity again, it is slowing down to zero, it's going backwards, and then it is staying constant again. And I've already kind of broken this up to where the rates of change of velocity are in these different sections. And that's rather important because a lot of times in this class we're going to look at constant accelerations, not changing accelerations, because acceleration is a change in velocity over a change in time. Am I on camera? Yeah. So wherever our slope changes, we're going to break that problem up, and that's pretty important to note. So taking a look, we got some object, I don't know what it is, but we're going to look at it piece by piece and then put it all together. So this first section here, we have this object moving at a constant 4 meters per second for 1, 2, 3, 4 seconds. So if you go 4 meters per second for 4 seconds, then by units, I'm not going to write up the units down there all the time because it's going to get a little bit confusing, especially when we use variables. But 4 meters per second for 4 seconds, we go 16 meters in total. Okay, and if you take that and take a look, we actually have just found the area of this very first rectangle. So the base is 4, the height is also 4, even though it doesn't look like the same height because I scaled it differently. We can just say, hey, base times height. The base is actually a change of time. The height is actually a velocity that we're at, and we're going to get something like 16 meters. Okay, not too difficult, but let's go on and look at these other sections. Let's go ahead and cover this one and this one first, these two first, because these are going to be just a little bit different. So taking the same steps that we just took to find the area, which is the displacement on your velocity time graph, we're going to look over here. I have some kind of rectangle. I've got a base of 1, 2 seconds because we go from 8 to 10, and we have a height of not 4, 1, 2, 3, 4, but we actually have a height of 8. Alright, so base of 2, height of 8, 2 times 8, we got 16. We should be going 16 meters here, using the same logic that we had for the first section. Last part, we got a base of 2. We got a height of negative 4. 2 times negative 4 is negative 8. Make sure you keep that negative there because we are going backwards in this section of the graph. So, easy stuff. We've covered the constant velocity things. It's like if you're running at, I don't know, 6 miles per hour, if you go for an hour, you go 6 miles. If you go for half an hour, you go half that, so 3 miles. Looking at these though, these are a little bit different because our velocity does change, and when our velocity changes, we have some kind of acceleration. Now that's not a big deal on a graph, but it might be a big deal on like a word problem where you don't have a graph yet. So looking at this, we go from 4 all the way up to 8 meters per second, and we covered a time of 1, 2, 3, 4 seconds. Now we could actually apply the same logic that we did over here, and over here as finding the area, but we don't have a nice rectangle, we don't have a nice triangle, we have both actually. And so what I can do is I can just look at it as a combination of shapes, and yeah, I can still do the area now. So I have a base of 1, 2, 3, 4. I've got a height of 4. 4 times 4, just like over here, would be 16 meters. So it happens that all these areas, which looking at the shape, yeah, it's the same shape, should be 16. Got to add in that little top though. That little top is going to be 1, 2, 3, 4, and a height of 4 again. So 4 and 4, that would be 16, but we're going to slash it in half because it's a triangle. And so this would be 8 meters. So for this middle section right here, we are going a total of 24 meters. So 24 meters is going to be our actual distance covered or displacement covered there. We can also talk about this thing called acceleration. Don't forget, that's going to be a change in velocity over a change in time. And I've got a change in velocity of up 4, and it's going to take over 4. So we have an acceleration, this would be a change in position. We have an acceleration of 4 over 4, which would be 1 meter per second, every second, meters per second squared. Okay, going over here, kind of the same idea. We have triangles put together. Let's go ahead and cover that acceleration first. And again, the acceleration is a change in velocity over time. Change in velocity here is going to go from 8 down to 0, and it's going to take 2 seconds. 8, negative 8, down to 0 in 2 seconds gives me an acceleration of negative 4 meters per second every single second. Okay. I know I'm talking kind of fast, but in these videos you are free to pause. Just don't forget that you're watching a video, so you can go pause it and go back, skip around. If you don't like what I'm saying right now, you just skip ahead. But be careful on doing that because you might miss an important point. Here's the acceleration for this whole thing. This is the constant slope, so -4 is all the way. And I'm going to find the area of this top triangle, which is going to be a base of 2. It's going to have a height of 8, and again, it's going to be that 16 for the total, but we're going to slash it in half, so that's going to be 8 meters here for that triangle. This triangle is going to be a little bit different. Got a base of 1, got a height of 4, so 1 times 4 is going to be 4. 4 divided by 2 is going to be 2, but let's go ahead and make that -2. Okay? And again, the same acceleration because it's the same straight line that we have. Well, looking at this, we've pretty much covered it all. We could go through and make another graph of acceleration versus time, or another graph of position versus time, but I'm not going to do that. We're just going to focus on velocity versus time today. And so, looking at the whole thing, we have a total of, look at all these 16s. We got 16 plus 16 plus 16 plus 8 plus another 8, which is 16. But then that's all of our positive stuff, 64. Negative stuff comes in. We got to do -8 -2. So we got a total displacement of, over the whole thing, 54 meters. And we have a total change in time of 15 seconds. And this is kind of important because we're going to look at one more thing, and that's going to be our average velocity for the trip, because our instantaneous velocities are shown by the graph itself. At this instant, 1 second, we're at a velocity of 4. But let's also talk about the average velocity. An average is going to be the combination of all your velocities, and the easiest way to do that is going to be the change in position that you go over the change in time. And since we just found that out, go ahead and take the 2, 54, divided by 15, and I get 3.6 meters every second if we were moving at a constant rate. Okay, so the average velocity is 3.6 meters, and ta-da, we are now into the portion where you say, hey, what are the equations to all this stuff? Because physics, I heard there are all these equations that we need to know, and these are them. Same stuff that we're going to do over here, or we did over here, except these are equation format. And in particular, I want to take a look at this one. The change in position is all this stuff, because can we apply that to this graph? And yes, we can, but we got to apply it per section. And so, before I even do that, let's go ahead and look at what sections we can apply this to, or which one would be the best to apply to. First one, we actually already did it, right? 4 is the velocity, note the v. 4 is the time, note the t. But what's the acceleration for the first part? Well, acceleration is change in velocity over time, so it's nothing. So really, this equation, we just took off the end there. So for all these constant velocity portions, velocity times time is what we did. And it just so happens that on this graph, velocity times time is the area, right? The velocity, the vertical, times the horizontal, the time. Okay? And you might be saying, well, what the heck is this? Well, acceleration, what is acceleration? Acceleration is the change in velocity over a change in time, right? And we got a little time squared next to this guy, and we got a little 1/2 here. Well, if we do some math, one of the t's cancel out, don't they? So we can say 1/2 the change in velocity times time. Oh, wait. This is just half of what we could have had there if we had a change in velocity. So that's just the area, which is why I was doing area over here with the triangles. So just to make sure it works, we're going to take this equation. I'm not going to use the other ones. We could, but I'm not. I'm going to take this equation, just make sure it matches up with one of these sections. Let's say this one. So for this one, my equation again is the change position is going to be equal to my initial velocity. This little v0 thing, initial velocity. It's going to be 4. And we're going to go for 1, 2, 3, 4 seconds once again. And I'm going to say plus 1/2. The acceleration for this, which we found out earlier, was 1. And then we got t, the 4 seconds. And we're going to square that. Well, I mean, just taking a look, is this math the same math as popping up here? 4 times 4 is 16. 4 squared is 16, but then we cut it in half, that's 8. And so we have 16 plus 8, which is going to be a total of 24 meters. So we're good, we're golden. Fantastic. Okay? Last thing, very last thing, is to say, hey, we found out that we went 54 meters, right? 3.6 meters per second. Just to double check, this mesh is really easy, should work out, but let's just do it anyway. The average velocity times the time, and for some of you, you're like, why are you doing this? It's right there. Yeah, I know, but for some people, we need it. Okay, we're going to take the 3.6, which is our average velocity, and if we had moved for a total of 15 seconds, yeah, we should get 15 times 3.6, we should get that 54. So math doesn't lie to you. Algebra doesn't lie to you either. It should work out. So easy, velocity time graph. Make sure you know how to work one of these. You could do the same thing for acceleration time. You can do the same things, well, sort of the same things for position time, except we won't be finding area there. But this is all for some random object going at some speed, speeding up, some speed, slowing down, going backwards, and some speed again. And eventually we get somewhere. In this case, we got 54 meters from wherever we started. That's the end of this one.